Alright, how's it going, party people? Welcome to the office hour with Dr. Alberto Cruz. I am your host, Dr. Alberto Cruz. Today's example is the well-known iterative solution to Fibonacci. Some premises for what we're doing here is going to be ARMv8, also known as ARMv8 in a Linux environment. Specifically, this is an EC2 A1 instance, and we're going to be using GCC and GDB. Another prerequisite for this video, we're going to be using only static variables today. We haven't really gone over how to use the stack as of yet. Alright, let's go ahead and get going here. What I'm going to do is use Vim to open up a .s file, .s being the convention for assembly files. And let's start coding this thing. I'm going to enter insert mode here, begin with a data section. In my previous videos, I discussed why I align it by 2. We'll have global n word 10. All right. Going back to our example here, note that n is initialized with a value of 10. All right. It's an integer. Now going back to our code here, we declare a global variable. It's labeled as n. All right. Remember that this is the compiler directive. It doesn't actually do anything as far as declaring the variable. It only means that the linker should consider this a global variable. And this is declaring the following word, which is initialized to 10, a decimal value of 10, as the label n. All right. We're going to want to repeat this for every variable that we have. Looking at this example here, we have quite a few variables. We have n, we have a, we have b, we have next. I also want to point out here, we have a variable for I, which is our loop counter. So we have quite a few of these things. I'm going to just speed through and create those variables because they'd follow the pattern for these 2 lines. All right, so going back to our example here. All right, let's go back and check our other variables. A should be 0, B should be 1. So let's check that there. I guess A is our first fib value. We'll start the sequence at 0. And then B must be 1. We'll start that at 1. Other variables that we have the concept of next, which is your temporary variable used to sort of juggle the values, as well as our counter I, which should be initialized to a value of 1. Going to the console here, we initialize a variable next. It doesn't have an initial value, so I guess we'll just set it to 0, not that it really matters, because an assignment's going to be performed on it. It doesn't require an existing value. However, I is our loop counter, and according to this solution of how we're going to implement our code, we're going to start the loop counter at I equal 1. All right. Okay, let's go ahead and get coding this with the rest of this thing. So what we're going to do is we're going to create a text segment, and we're creating a global variable, or I'm sorry, global function called main. And I'll go ahead and enter our return 0. All right, so that's the template for our main code, what you see at the bottom there. We're going to start inserting our code now. If you've been watching the rest of the videos, you know that what I like to do when I'm dealing with static variables is to set the pointers at the beginning of the code. So we have quite a few variables here, so we'll just set them in order here. So this line of code says to set the register x0, 64 bits. Remember that ARMv8, all pointers / memory addresses are 64 bits, and set it to point to n. All right, we're going to repeat this for every single variable. All right, so we have 5 variables we're working with: n, a, b, next, and I. And I want to point out here, if you're concerned, like this seems like a lot of registers that we're using. Technically, you have 32 with ARM, although the temporary registers go up to 15. We probably still have enough free registers to just sort of leave those registers permanently in our code snippet as pointers to these variables. All right, so let's implement our loop here. So as far as our code goes, we have a couple parts here. We've got the loop test criterion, the I++ part, and then the loop body itself. I want to point out that with our compiler or linker directives to initialize the value of I, we already handled this part of the code. The I is equal to 1. So I guess the first thing to do is to handle that inequality. Remember that in ARM, or in any assembly language, if the conditional is true, it jumps, which is the opposite of what you'd expect most high-level languages to do. Okay, so looking back at our test here, it is I less than n as the criteria for continuing to continuing to execute the loop body. So we need to invert that to refactor it so that if it is true, to quit out basically and to not execute a loop body. All right. So if that's I less than or equal to n, what you're looking for is I being greater than n. All right. Let's go ahead and code that. We need the value of I and we need the value of n. We already have the pointers to that, so that's two LDR instructions. So it's LDR. Let's get I. I'm going to put that in W5. All right. Let me fix that. W5, and then we want I, which would be the pointer in X4, and we want N, which would be the pointer in X0. All right, we'll use W6 for that. And then we want to compare them. Compare I to N, and then if it is greater than, jump to a particular label. So notice down here, we actually need two labels here. We need a point that indicates the end of the loop. So I'll also label something as loop bottom, basically, and that would be our concept of returning 0 there. We want to quit out to loop bottom if it turns out that I is greater than n. All right. The other part of the loop that we have to implement is our I++. All right. This is our typical load store sort of deal, where if you wanted to manipulate the variable, you have to load it. All right. I'll just put that here in W5, and we will add 1 to it, and we will store it back on the pointer X4 being I. All right. Hey, so I want to point out here, we dereference I at the start of the loop, and here I attempt to dereference it again. Actually, we can probably remove this line of code and just comment it out, so long as we're careful here and we don't modify register W5 inside of our loop body. All right, that value will stay there as long as we agree to not mess with it. Okay. All right, so looking at our code here, we're all good with this. We're all good with this. Now we need to implement the loop body. All right. So let's start by maybe writing down what we have to do. Next is equal to A plus B, and then we have A is equal to B, and then we have B is equal to next. All right. So if we're doing this A plus B, we have to dereference A and B. So that's another set of LDR instructions. I'm going to go ahead and cut and paste from up here. This time we're going to dereference A, which would be X1. I'm going to put that in the temporary register W7, and let's cut and paste that again. Let's dereference B. I happen to know that's in the pointer X2, so that means that A is in W7 and B is in W8. And what I'm going to do here is add W7 and W8 together, and I'm going to store it in W9. Remember, it's a right to left assignment, so you read this as W7 plus W8 is equal to W9. And then don't forget to store that, right? Load store architecture. The register isn't the variable. You have to now put that back into our variable for next, according to our comment here. The pointer to next being an X3, which you can see up here. All right. Okay, so that's that code. Next line of code is to assign A a value of B. So you might think to dereference B, but I want to point out that we already did that over here. And looking at our code, we did not modify W8. So in my opinion, it would be uncalled for to dereference W8 again. So we'll just store whatever is currently in W8 on our pointer to A, which, looking up here, that's X1. All right. So X1, and then so that's pretty much it. That was assigning A the previous value of B. Now we need to assign B the previous value of next. I want to point out here that I stored it into W9. So even though I pushed the value onto the pointer for X3, between here and here, I haven't modified W9. So W9 should still be containing that value of next. Let's just go ahead and use it. And then just confirming again, A was located in, or it's B, sorry. you need to put the value onto B, which is X2, okay? All right, so X2, okay, cool. That pretty much is our code, people. So let me just clean up these comments here, and then I realize it's a little messy, okay? So this right here is our A plus B. This right here is our A equal to B. This right here is our B equal to next, and let me insert another comment here that this is I plus plus, noting again that we didn't dereference I because we did it earlier at the start of the loop top. All right, and then at the end of the loop body is an unconditional jump to bring you back up to the loop top, which should determine if you should keep looping or not. All right. Okay, so let's compile this thing and see what happens. All right, cross your fingers, people. All right, it ran. Just run it. So I compiled it and I ran it because, you know, with loops you might get an infinite loop, and I wanted to make sure we didn't have one of those. Let's bring it up in GDB. Okay, all right. So what is the point here? The point is that we want to get the nth Fibonacci number. Let's go ahead and print what n is. It's an integer pointer for the address of n. So it's 10. What is the 10th Fibonacci number? Let's set a breakpoint to loop bottom. All right. The reason being is a loop bottom is that ending curly brace, and we should only ever reach there if the loop decided it would terminate. It's just before return 0. It should have the final value of whatever nth Fibonacci number you want in B. Okay, that's the number that you read when you want the final value. All right. Let's go back to the console now. Now we've set our breakpoint. Let's run this thing. Okay, now let's check the value of B. What is that? 89. Cool. Yeah, that's the Fibonacci number we needed. Looks like this thing works, people. If I go back here, actually, I think there might be one or two optimizations we might be able to perform on top of this. Let's just think about this. So we dereference I, we dereference N, you know, that's fine. Actually, I think the main issue here is the concept of next. Because next is just a temporary value. And if you watch that video on variable swap, it turns out that the existence of registers make the thinking process kind of weird in terms of your ability to swap variables. Next can exist entirely in a register, right? You could actually have done A plus B into a register and not needed to store it onto next, because these operations will actually still be fine, even if you note that if I delete this line here, like if I comment this line out entirely, this operation will still refer to the value of B, and this operation will still refer to the addition of the old version of A and B. So at the assembly level, next is not even required as a variable. Although, if you were to eliminate it, I want to point out here that these are optimizations, and the premise is that we're supposed to be implementing this code as given. I guess the idea is that there must be a variable next that you'd still have to implement. So whether or not in whatever environment you're in, you'd still want that to have that variable, I'm not sure. Like we can't say, you know, later on do they use next? I'm not sure. You know, it would have to be whatever context that you're in that sort of thing. So anyways, um, that was iterative Fibonacci. Next few videos, we'll be doing some linear search and maybe a recursive Fibonacci. All right. Have a great day, everybody.